No, we can do this. Okay, that's good. No. Se non sono
The question is, do we really need a new link? Can't we use this one? There is one person.
To go on the M17 stream, no?
So this is the one.
I created another one, which is actually streaming right now.
Okay, but...
So let me manage that one.
But...
But from here, once okay, we are live, let me share.
Which just enjoys playing with the radio electronics, with coding firmware, and maybe wants to get closer to the world of the radio. So it's not only for licensing of upgrade operations, even though having the legal license is a nice feature to have, because then you can transmit freely on the main event which were designated. So yeah, OEM is hosting the event, and we'll be talking about open source, the open source philosophy applied to two different aspects of which is the development of firmware for existing transceivers and the development of digital voice modules which are free and open source. And I will talk about, give an introduction, and then talk about OpenRTX, which is open source firmware development effort, and then I will give the words to our guest, which is Wojciech, which is the creator of the M17 Project. So, without further ado, let me begin. So, for you are not so let me start from the absolute beginning with a very simple primer, so that we can have a graphical understand. So let's say that you want to transmit some information along an RF channel, a radio frequency channel, so from one radio to another radio, okay? The way we do it is we use a modulation scheme. So we have, we start from a carrier wave, which is just a sine, okay? And then we add some properties of this sine wave to convey the information to a different device which is listening to this transmission and can detect and sense the changes of the behavior of this carrier wave to retrieve back the information which we want to transmit. Okay? So, in case of analog modulation, if the signal is, in this case, this very low frequency wave here that we want to transmit over the radio channel, and we want, for example, we can, so we want to transmit that signal, we have our carrier waves, and we can alter, for example, the amplitude of the carrier waves, producing the so-called amplitude modulation. So, as we can see here, the carrier wave, which is this high frequency signal, gets its amplitude lowered and again rise again according to the value of this analog signal here. So what we get here is this resulting signal, and AM radio can detect this carrier and can extract back the analog signal. Another analog modulation that we can use is a frequency modulation. So we are altering, instead of altering the amplitude of the carrier wave, we are altering the frequency of the carrier wave. So this is the result. We have the frequency which gets a little bit higher than the carrier or a little bit lower than the carrier in a continuous analog way. And again, this is another way in which we can convey analog information to another way. And AM and FM they are different. They have different behavior, which are given by the signal nature of the two signals. For example, the AM signal juxtaposed each other, FM does not, and FM is in general more resistant to noise. But yeah. Anyways, both are used even nowadays. FM for radios, for commercial radios, and for many other purposes. AM, for example, for airplane radio control communications, but also for commercial radio. We have still radio, which is transmitted in Milan. So, we saw the analog modulations in which we are conveying an analog signal. But we are, what if we want to convey a signal which is digital? Because nowadays we are used to processing digital signals. We know that when we switch into the digital domain, many things become way simpler. For example, compressing data, storing data somewhere, transmitting it over the internet, so on and amplitude, using a digital signal, we can modulate the phase of the signal, or for example, both the amplitude and the phase. So the advantages of using a modulation which is digital are several. For example, digital modulations allow to apply all the well-known art of error detection and correction codes. Okay, correcting codes on an analog signal is probably impossible. On a digital signal, we have a well-established art where we know we have many codes that are already well studied and can be applied. So this means that basically we are able to detect that the transmission error happened, which is nice because, for example, we can request again a new transmission of the same data, so that we, in the end, we get a data which is another. Or we can even have to do something which is called a forward error correction. So we are able, with some modulation scheme, some coding scheme, we are able to, by adding some redundant information to the payload and transmitting data on the way, we can have the receiver correct autonomously some errors in the transmission, even without requesting a transmission, which is good for the latency for real-time applications. Another advantage of using digital modulation is the fact that we can, while from the other part, we were only conveying one signal, for example, voice or video or analog video. In this case, we can very easily transport heterogeneous data. We just need some data which is already in digital form. For example, we have an MPEG stream of video, an AAC stream of audio. We finally multiplex that into the channel and we are done. So it's very easy to mix heterogeneous data as long as they are encoded in binary. And also it's very easy to build hybrid radio frequency to internet networks, because you can pull out data from the RF, the data is already digital, and you can take the packet in a suitable format and send it to our internet, which is convenient because it makes it easier to, for example, the RF is very funny and nice, but it has its own limitation. For example, you need to have good coverage, and while if you use a hybrid RF plus internet, you can even reach the other part of the globe just by relying on an internet-based bridge wave. So, digital protocols are more or less mean that they have a physical layer. So if you are students of the Polytechnic and the networking course, you know that we can represent networks as layers. And we have a physical layer which has the scope of sending over bits of information by populating a carrier and eventually correcting or detecting errors. Then we have a data link layer which takes the stream of data and it arranges that data either in stream, which is good for basically real-time data, or into packets, maybe if we want to use some messaging system. And then finally we have the application layer. Again, we are skipping many layers from the standard ISO policy stack because just in a course representation. But on top of the data link layer, we have all the application that we build that we use the underlying data link. And there can be voice communication, data communication, metadata sent along the way, and so on. So, when using a radio channel to increase basically because the radio medium has the characteristic of the fact that only one person can use it at a time. slightly different fields. Or we can do time division multiple accesses in which we decide that basically every, I don't know, 40 milliseconds, a new actor can use the channel. So you divide the time into slots, and each slot is assigned to a user. And variations of then we have a code division multiple access, which is more complicated and relying on the modulation itself scheme to enable more people to transmit simultaneously. A combination of these three is used in any of the digital protocols that we use nowadays. For example, LTE has a slotted, both a channel-based and slotted-based system. So each cell has a limited number of slots. And if you have too many people in a square, in a net, you don't get internet access anymore because maybe that number of slots was completely filled up. So these are used not only in the protocol that I will show, but in general and in digital operations. As I said, we have basically in digital walls, we have our payloads, so the actual information we want to convey, and then we have some additional information that we compute that and we can send that along the way, and that allows either to detect errors or to correct errors. And when you design a protocol, you have to suitably choose the correct set of detection and correction codes, because you don't want to waste all of your bandwidth by sending error code, but as well as you want to have maybe some correction power. So you might want to be able to correct at most 3 bits every 90 bits and something like that. Okay? So you have some tolerance as well, which is good because in the end, when someone uses your protocol in the wild, for example, let's say it's a voice protocol, digital voice protocol, and some noise appears, okay, maybe you get some transmission or you move out of the way and so the transmission is noisy. If you have error correction, for example, you won't, if you don't have error correction, you will hear some weird ugly noises in the voice because the errors propagate out the way to the voice channel. While if you have error correction, the code might be able to fix those errors. So you get an overall better experience, even in a harsh condition. Okay? So basically, we have you will see it later on. So let's consider, for example, the application layer. So we have our protocols. We have at the application level, we see a channel of information. Okay, so we are able to send some data to some recipient. Okay, and we know that that works, just works. We can simply ignore whatever everything that lies beneath. Just as we use the general TCP/IP networks, where we don't care whether the link is made of Ethernet, broken ring, or whatever. We just use it, and we hope that our packets will go towards the end. If we are using TCP, we know whether the packets will go towards the end or not. So let's say that we have this digital channel already in place. We could do some very interesting applications on top of that. For example, well, you can do voice, which is nice because we are humans, we enjoy talking with other people sometimes. Sometimes we don't enjoy that. In case we can do, there's voice there. In case, for example, we might enjoy more typing than speaking, we can build an SMS system on top of that channel. Okay? Or we can, for example, build the geolocation inside our protocol. Geolocation is very open, some very interesting, basically some very interesting scenarios because in general we tend to be, one may think, why would I want to share my own loading those into a centralized service which logs the tracing. So for example, this was a hike I did last summer in the Alps, and I submitted this signal to the neighboring receiving towers using my radio, which is equipped with a GPS antenna, and so I'm able afterwards to have a trace of the points where I was able to transmit. I can later understand which station received my communication, which is curious because maybe some very fast stations, okay? And I can get the altitude profile, which is also interesting. And yeah, so. But there are also other application services we might be nice to rents, like file transfer, okay, where you can basically send whatever you want, which might be cool. For example, if you have your radio has maybe you build a camera, you attach a camera to your radio, you can send some pictures along the way. All of this can be done. Most importantly, this might seem something that we are very used to have at hand in our smartphone. But let's remember that if we do this on a radio protocol that we build from scratch, we become independent, really independent of the traditional 4G and 5G networks, which might seem pointless, but actually has many advantages. There are situations and places where you might not rely on existing infrastructure. For example, in cases of war, even the dramatic cases of war, the communication network are the first target of any offensive attempt, because that's the way to disrupt the organization between people and to eliminate the chance of information. So there might be extreme cases where you don't, or even in the case of natural events where you don't have that. But even without going that far, if you are hiking, it's extremely common to find yourself in a place without some coverage. But due to the nature of the radio transmission, it's in the mountains, it's very easy instead to get access to a radio network, because while the cell towers tend to be directed towards the bottom, because they tend to be focused on a certain area of few kilometers of radius, the hub structures are instead, they tend to have a non-directional coverage because they want to get as far as possible. Okay. As well as there is more fun and educational part of that, because if you are doing, since we are talking about open source protocol, if you want to build, I don't know, the auto discovery service, which allows you to, from your radio, understand which are the services available on the network that you are connected to, you can implement that yourself. And you can learn all the details about how that works, you can use your fantasy to build some interesting scenarios, and so it's something you can really own, even the problem. It's something that you cannot do with commercial 4G and 5G networks, where you are just a user and you cannot touch at all the service. So, an important piece in the digital voice communication is our coder. Our coder is a piece of software that takes an analog signal, typically in the voice, the analog representation of the voice, okay? And it converts it into without paying a license to the VSI. And if your radio used it, this means that the manufacturer of the radio paid a license for that. And but if you build your radio yourself, you cannot use it. If you build a software, you use an SDR, software-defined radio, with your PC, and you want to modulate that protocol, you cannot use it because you need to pay for the license, which is a showstopper if you want to expect it. However, luckily there are some open source alternatives. One of those is Codec, which was made by David Rowe, and it's used in two protocols. It's 3D, and which is a low bandwidth protocol made for HF communication, so very short frequency below 30 megahertz, which typically channels carry only a few bandwidth, but they have the advantage that they bounce over the atmosphere. So with an HF link, you can go very far away. You can directly connect with the United States or Asia without any relay, just because the wave naturally propagates between the atmosphere and the Earth. And so let me basically, again, for the SMS service, which might seem something that is so 90s and we don't need it anymore. In fact, if we think about implementing this from scratch, it can be fun again. For example, we can, if we have an SMS on their own, it's good. We can send text messages to our fellow people who have their own radios, and that's okay. But let's, for example, introduce a different use case. What we could do is we could, for example, repurpose an old pager from the 90s. We can, either we can, if we can get one which is still alive from the 90s, or if we can get a Chinese version which is still manufactured nowadays. For example, they are more common than you might think. The pagers, so devices which can receive text messages but receive only. For example, when you go to a restaurant, well, let's say a street food restaurant, they give you the token that vibrates when it receives your hamburger is ready. That thing is using the same protocol as the 90s. So, yeah, if you build, for example, if you build an SMS application, you can bridge that with your pager network, and you can, for example, be able to ring the pager of your friend, which is a very cool thing. It's weird, but it's also very fun to do. And or you can, for example, even make your own token at the restaurant, ring before the hamburger is ready, and then go there and demand for your hamburger if you don't need something. But yeah, let's not do this. Please keep it legal. So finally, for data modes application, there's many applications we can do. Let's remember that typically the scenario that we have is well, we can either have a simplex transmission between the two radios, each of my friends has its own radio, and they are somewhere around the city, and maybe I'm able to reach them directly. But this is not easy because radio frequency propagation is peaky, and whenever we have, for example, we are in a city like Milan where we have several buildings, it's very hard to get a good channel between two individual radios. So what is usually done is that you typically take a bigger radio, something like this. You take a bigger radio, you start two of them, and you put it on the top of one. And by doing this, you are exploiting basically the fact that comes here in plan, and it's very easy to activate those. We can even try it. It's very easy to activate those, regardless of where we are in Milan, even with a short antenna like this and less power, because the mountain is high, so it has there's not so many obstacles between the mountains. So if we build the repeater of mountains with the capabilities of our digital protocol, that opens some very interesting use cases. For example, we could connect that repeater to the internet, okay? And we could have it, for example, send firmware updates to the radios. Firmware of a radio is it weighs like around I don't know 2 megabytes, I think. So maybe in 5 minutes of transmission, you can get a whole firmware package and you can update your radio on the go. Or you can, for example, here is a problem. I will show you a bit what they are. That's a very interesting application. We could build a data link layer. So we could build another interface between TCP/IP, or let's say just IP, because TCP works very well with channels. IP and our digital protocol. We could do that. We just need to build a way to encapsulate the IP frame to break for example, the Ethernet frames, which are very long, into shorter frames. Therefore, that we can set it in our protocol, and we reconstruct everything and to map destinations to radio destinations to IPs. Okay, but if we do that, we can connect at the radio to our laptop, and maybe build an emergency network in a remote place, and then have our own laptop collect some telemetry and share it with a network of other computers. Or for example, if we have a sensor, a weather station somewhere, we can have that weather station send digital data to other people which are listening to those transmissions as well. This opens to many possibilities, and really, very many cases, your fantasy is the limit, and then the amount of hours you can use it to implement. The possibilities are very, there are a lot of possibilities. So I will keep the amount of possibilities. Let me talk about, let's just talk about the last So, most of the, basically, I'm talking about digital protocols as if we were making it from scratch. However, there are some existing digital voice protocols for radio, for example. One of these is called DMR. DMR is different from DMR. DMR was created by Motorola, which is a giant. It does many things, but among those, it's very important in the radio industry, for commercial radios, for firefighters, police department, everyone that needs a commercial system. They developed their own protocol, giving it a sample name Moto Turbo, and then basically that protocol at some point became a standard. So ETSI went there and took the protocol and it made it a standard. DMR basically is very widespread. You have several radios on the market, even very cheap ones. For example, there is a DMR radio. The cheapest DMR radio probably is 35 euros on the Chinese market. You can find some decent radio for 50 euros. This is a very good radio, still Chinese one, and it costs like 100 euros. So, it's not that pricey to buy the equipment because we have many many models available. And it does frequency shifting, so it changes the frequency of the carrier. internet-based system which is called Brandmeister. And that system is cool because it's a global system, it's worldwide. And from that system you can, for example, interconnect with people using DMR in the US, or in Russia, or in South Africa. Or you can even send SMS or call a single individual person using that system. It's a federation of different emitters. And it's very cool. I mean, that capability is very nice because it allows you to simply, just by having a radio in your hand and talking with a repeater, so in theory, without even having a 4G connection, 5G connection, wherever you are, if you're able to connect with a repeater, you can talk with people all around the world, which is very interesting. So, there are many other problems like the bar, and there is a problem with the Hungary of the fact that there are like 4 very common protocols, and so you get that people, there is fragmentation, so people split between all the protocols, and you get all the protocols are not interoperable, and so you have to choose, very carefully choose, or so I buy a IS radio which does system fusion but does not DMR, but all my friends are on DMR, so I need a DMR radio. But I would like to use this star, which is another protocol, but I don't have any this star repeater nearby. So you know, this is a pain because you know, there are not that many of the ways. So if you spread them out on several protocols, you lower the chance of having some conversation, some meaningful conversation. And so this is also a problem. Luckily, there is basically this board, which is called an MTVM, which, as you might recognize, it looks like a Raspberry Pi, because it's meant to stack on top of a Raspberry Pi. And this one is able to modulate and demodulate all of the protocols that I listed above. So you can buy one, you can put it in your own home, and you can use that, for example, to use DMR radio to access the internet network of another protocol. Okay? Or you can use one of those to transmit to a pager. Okay? So it's an interesting toy to play, to start playing with radio protocols. And there is a ton of software available as well. They're quite easy to use. And I will briefly mention M17 because of the second half of this talk will be only that. M17 is an emerging digital bus protocol that was created by this guy here, and it's really getting traction right now. It's a very young product. It's only 3 years old. It's only 3 years old, which is very little for a protocol, because then you have to design it, you have to test it, you have to design every layer from the physical layer that you have mentioned, and you have to make sure that everything works, you have to code the software, the radios that do the protocol. So right now, the protocol is ready, and we are at this development stage where we are trying to create some devices which modulate that protocol. And something is important because it's open source. It's free and open source, so the specification is completely public, and all its implementations are open source. So with this protocol, even though the specification is one, okay, so you cannot just make your own protocol. The sense of having a protocol is to have a common standard so that devices can be interoperable. Okay, so you need a standard, but still the protocol is community driven. So several of the features of the protocol were will never run into some patent issue with this problem because it's designed exactly for that purpose, to not to put any legal or patent or licensing constraints towards implementation. This is an example of how M17 looks like when they modulated it with a standard radio. So you have, yeah, you will see this in the and M17, even though right now the radios that do M17, there are only a few of them, and not yet commercially available radios that speaks the protocol. For example, the fastest way to try the protocol is to use M17 on IP. In fact, M17 is a digital protocol natively has an IP-based interface. So, by using the DroidStar application, which is available for Android, or the TubeStar, which is the equivalent for Linux, you can right away modulate the protocol on the IP. So you will not be using an ARRL link, but the protocol itself will be encoded and it will be sent over an IP. Okay? You can do that already. You can use the voice feature of that already. And maybe we can show also a demo of that. Lastly, I will show you what basically the most important part of the open source development, software development in ARRL, which is OpenRTX. So OpenRTX is a free open source firmware for digital radios built by me, Silvano, which is there, and I will show you guys. And it was born because we were able to get radios like this for for a chip, and this radio has a decent hardware. It does a decent job for modulating signals, receiving signal. To display is a bit small. It looks like it's get out from the 90s, but still the hardware was nice. But the software that came with it was unbearably shitty to use. It was so badly written, so full of bugs. It didn't allow you, for example, the stock software does not even allow you to select the frequency you want to transmit from the radio. You need to use a laptop and use a software which runs only on Windows, which is hard-written Chinese to set your frequency channels and then flash the rate and then you can transmit. So we felt like there was this great potential which was lying in a device which is commonly available, and we were trained in the mindset of open source where the community can basically get together and develop some software which is shared with open source licenses so that it can force to be shared. And by doing that, we knew that we could, by starting some software development, I think we knew that we could unlock some features that are available. And we did it. Basically, this regular supports the firmware. The development started 2 years ago, and now it's in a fairly mature stage. We support basically several radios. We support 5 models of radios. We even can build OpenRTX for Linux to test, to develop faster. We did several things. And basically the two main goals of our projects are to enable hubs and other people which might be not hubs, even if they cannot transmit, they may still enjoy the project to implement, basically to experiment with their own ideas. So if someone wants to, for example, I know how to program, I have my radio, I have this idea in mind, but with OpenRTX you already have the building ground ready for you where you can put just your own function. free expression to their own ideas. For example, I don't know, someone tweeted 3 years ago that he implemented the Comic Sans font in Braille just for fun, but he was able to do that. And that's just a simple example. Ourselves, the core development, we are devolving most of our development effort into implementing cutting-edge technology, because we know that we can do groundbreaking things by having our own software platform. And some examples of what we did, the two most notable examples, for example, are M17. So we took the M17 protocol and we adapted an existing chip DMR radio to run that protocol, which was tremendous engineering effort, because we had to, this unfortunately requires a hardware modification, a small hardware modification of the radio. We have to remove a bar resistor and put a wire. But still, we were able to take a device which was hard-coded meant to do one protocol, and we enabled it to do a totally different protocol, which is open source. And this basically made it the first digital radio which supports M17. And this is one nice example. But just as we implemented M17, you can do all of it, because we are doing that in software. So you can implement a decoder and encoder for any protocol you can want. You might want to implement a transmitter for again a pager, or you might want to do a transmitter for I don't know, a packet. There are many protocols around which you might be interested in implementing for fun, for example. Or another thing we did was actually a contribution from the community, is the ability to track satellites. So I will show you a video that is worth more than 100 words. So this is a firmware that is running on Linux integration. As we can see, basically, here we are selecting some satellites from a menu, and the firmware is showing us the predicted path, the next path of that satellite from our position, our GPS position. And it will tell us the elevation of the path, so how high will be the sky, the hours at which the path will happen. As you can see, there is a full-fledged sky map. It's very faint, but you can zoom in and you can see the most relevant stars in the background. And all of this is idiotic. And for example, this is very cool if you are a ham radio operator, because there are some satellites which were thrown in the sky throughout the years, and they have a lower orbit, so they revolve around the Earth, and they go, for example, from one horizon to the other horizon in 10 minutes. Okay? And most of these satellites carry a payload which acts as a repeater, just like the one now. But they are up in the sky, so they have a very wide coverage. So what you typically do is you mount a big antenna like the one in the power bank that we're going to show you later, and you go somewhere where you can have a clear view of the sky, and you wait for the satellite, the right satellite, pass over your head, and you can use your own radio to track the satellites. And the coolest part of it all is that, for example, these satellites, they move fast. So they are subjected to the Doppler effect, because they are transmitting in radio frequency while they are moving. So when they are getting closer to you, the frequency rises. When they are getting away, the frequency lowers. Okay, this is a problem, because if you want to receive, you need to adapt the frequency to properly receive the carrier, because the carrier will move spectrum. As well as when you are transmitting, you are subject of the same Doppler effect, because there is a relative movement between the two objects, so the satellite will hear you with lower frequency when it's going away and so on. And this software can do automatic Doppler correction on typically this setup involves having a laptop with the prediction software, mobile phone, and manually correcting the frequency is very painfully processed. You have to be allowed to do so. But with open source software, you can do everything on manual. And other features that we want to achieve, for example, the next thing we will integrate into OpenRTX is voice prompts. So the ability for the radio to speak up the entries of the lecture shown on the screen, which is a critical feature for blind ham radios. And there is a big community of ham radio operators over the world which are blind. And the problem with them that they face is that commercial radio don't implement the voice prompt. There is one radio which is commercially implemented, but it was 600 euros. And in general, they don't implement it because it's an effort to do that. And the market is so small, it's relatively small, so they cannot get enough return on investment. So by building the voice prompt, on this we are getting the help of a very talented developer, which is a blind operator as well from Australia, which by putting the voice prompt inside this filter is enabling all the ham radio operators around the world for a chip to get one radio which they can actually use, which is a very good thing. And we can support, since we are building our framework with modularity, now we can support many different devices, even new devices, new radios. We can support new protocols, whatever we want. And so yeah, there are many interesting things that lie ahead of us. And finally, 3 steps. So if you don't have one yet, get a license. We need to double check that, but usually when you have an engineering degree, even a third-year degree, a bachelor degree or technical, you can go to the ministry and you can demand for a license. You just have to pay a small, you cannot do that anymore. So there is a example you have to do.
You have to do the hard copy.
You have to leave
regulation.
Thank you for the question. So there is a very small example of technical stuff, but very easy. Like, what is a resistor, what is a calculator. Some stuff to start. You pass the exam, you pay like 14 euro of taxes once, and then every year it's like 5 euros of taxes. But I'm not kidding, 5 euros, that's it. So it's very cheap. And you get a fancy paper license, which is, it's very good to show to your friend, hey look, I am a ham radio operator. Yeah, I know, I'm cool. And apart from the actual physical license, you get the possibility, the legal possibility to transmit on several bands, from shortwave to VHF, so 140, 430 to millimeter waves, gigahertz band. There are so many bands which you can use
So they say that the audio is crap from... hanno detto che l'audio fa schifo da Twitter, quindi lo metto più vicino.
Nicola already told you what M17 is, so it's an open source digital voice protocol that has been designed by hand and open. So it's very important that we are not, we don't have to rely on any manufacturer. So we can just say, we want our specification to look like this. We want M17 to be able to do that, and there is no one stopping us from doing it. So we just decide what we want in the protocol and how we want to do it. And M17 was created as a response to a growing community of digital radio users in Poland, because it was created in Warsaw, in Poland. So we wanted to experiment with digital voice modes, and we were already interested in DMR and Tetra. So we wanted to try something else. And we were tired of MD and ACELP voice coders that are used in DMR and Tetra. So we tried to experiment a little bit with the digital voice modes. And M17 actually started back in 2019 as a weekend project. So I just took some breadboards, some STM32s, I ran the Codec 2 on it and just started experimenting. And back in 2019, I used RFM26W, I believe, modules, and they are just used for 433 megahertz band, so one of the ISM bands. So I used that to transmit M17 3 years ago. And now M17 has grown into an international team, and it's an international effort to proliferate the specification, protocol, and hardware. So 3 years ago, it was just a weekend project that extended to an international effort. And one of the aims of M17 is that we want to bring back experimentation to ham radio, because right now you can buy a DMR radio, but actually you can't do much with it. You can just use it as a DMR radio, and you can refresh it with OpenRTX, but not every radio supports it. So you can't really change anything that's inside DMR. You can just use it, you can just buy the radio, use it, and nothing else. And M17 is an answer to that. And as I said, and as my friend Nicola said, Codec 2 is the voice coder that is used in M17 and 3DV. 3DV predates M17 by a few years at least, and 3DV was mostly used and is mostly used for HF bands. And also 3DV supports 700 bits per second voice bit rates, which is very low and doesn't really, it sounds good in comparison to SSB modes. It sounds good, but still the rate is low. So the answer to that is M17, which uses VHF and up, and we use higher rates like 3200 bits per second and 1600 bits per second, which is a little bit higher, and that results in considerably better voice quality. Now, I'm going to refer to the specification document that is available online and for free. And if you visit that page, you can just browse through the documentation, and right now, I believe the specification has 60 pages. So it's not a very short document, but it's written so that it's very understandable. So, of course, you have to have some base knowledge on mathematics and maybe DSP, but still the basics are there, so you can just read it, and I believe you can understand it, what's going on in the protocol. Now let's focus on the features that make M17 something different than DMR and NXDN, D-Star and other modes. So the first one and the most apparent is that IDs used in M17 are not inside some black box like a central ID database. So actually, when you are a ham radio operator, you've got a call sign, and your call sign is unique globally. So if we've got India Uniform 2 Kilo Whiskey Oscar, that's only one in the whole world having that call sign. And SP5 Whiskey Papa, that's me, there's only one. So why should we use any IDs that are required to use DMR, or at least are, you are supposed to get one to use the network, because if you fake your ID, that's not a good idea, but it's doable, but it's not recommended. So in M17, you can just punch in your call sign and use it as your ID. So there is no need for any database, so you don't have to register anywhere. Then, in analog FM modes, we've got something that's called CTCSS, that stands for Continuous Tone Coded Squelch System. So when you want to have more than two parties using one frequency, using analog FM, you can assign to every party one distinct frequency that is unaudible, because it's below 300 Hertz. So radios know when to unsquelch the radio and just receive the signal. So when the tone is present, you can say that Nicolo is transmitting to me and Silvano can't listen to that communication because he's in a different party. So in M17, we've got something that is called the channel access number, and it works much like the color code in DMR or the CTCSS from an analog signal, analog FM. So you can have at least two parties transmitting at the same frequency, but not at the same time. So you are using the same frequency, but you can't hear each other because you've got different CANs. Then something that's very important, and it's also available in DMR and other modes, is that we support encryption. But it's very important to notice that encryption is disabled by default. So normally, in most of the countries, encryption and amateur radio doesn't go together, and it's illegal to do so. So normally, you just don't touch that setting. And for example, in Poland, it's not illegal, so it means that it's legal and you can use it. So in Poland, you can turn it on, but it's not very welcome on repeaters. So encryption is not really welcome, but you can use it for DMO operations. So that's a direct mode of operation. Okay.
In Italy, is illegal. So just to have
Yeah. In most of the countries, it's not legal to do so. Then we've got packet and stream modes. And normally, if you want to talk with someone, you are probably going to use the stream mode, and you are going to stream the voice data from A to B. And if you want to send an image, a file, or your geographical location, you can just use the packet data just to send a burst of data and forget about it. And then lastly, I've heard many times that when you get a DMR radio, it's a pain in the to configure it and to use it like the Anytone 8878, for example. That's a DMR radio. So I suspect that radio can be just configured using the keypad that you have. But most radios don't have that. So if you want to configure your radio, you have to use a special software that is released by the manufacturer, and it's really pain in the to do it. And in M17, you don't have that problem. So you just punch in the frequency, the channel access number, your call sign, and the recipient call sign, and you are set probably. Then, the address encoding. As I said before, we don't rely on any database that link your call sign to your ID. So you can just punch in your call sign into the radio, and M17 knows who you are. And this is how it works. So we just take the call sign as a string of characters, and we assign a number to every character, like when you write a number, for example, 123, you've got 1 hundredths, 2 tenths, and 3 units, right? And it works the same in this case, but in this case we've got an alphabet that is 40 characters long. So instead of 10 or 16 in hexadecimal, we've got 40 characters to encode the call sign. And there are two examples below the table. So for example, AB would be encoded into 81 just because A is the first letter, so it corresponds to the value of 1, plus 2 times 40 because it's base 40, and B is 2. So we've got 81. And for a more complicated example, we've got M17 encoded into that value, 55533. So you can check the math, it should be okay. Then, the physical layer. So if you are not sleeping already, you are going to go sleep right now. The physical layer is 4FSK, just like Nicola said, and what is actually good about M17 is that the signal is 9 kilohertz wide. It's not 12 like usually the analog signal is 12 kilohertz wide, and the channel is 12 kilohertz, but in M17 that's 9 kilohertz. So we've got the same energy that we would use to modulate a wider channel into a narrower channel, which is very good because we've got better power efficiency using just narrow channel. Symbols per second, that's 4800, so that gives 9600 bits per second gross. That is the bit rate that goes through the RF medium. So you have to deduct all the error coding, all the overhead that is used for correction and stuff like that. And we also use FDMA, which means that you can use one frequency for one user. And if you want to have 2 users, you have to use 2 different frequencies at the same time, of course. Now, how the transmission looks like. So, in this example, we've got the time advances from left to right, and at the beginning we've got a preamble, which is just 40 milliseconds of, at least 40 milliseconds of a 2.4 kilohertz tone, and this just denotes that this is the beginning of the transmission. So it does nothing else. Maybe it's also used to ramp up the amplifier that is used in the radio, so it can just ramp up to the nominal power before we start the transmission. So it actually has more than one usage here. Then after that, the first frame that is being sent, because we send data in frames. Each frame is 40 milliseconds long. So every frame starts with a sync word, which just tells the receiver that here's the start of the frame, and whatever comes after it is the data that should be received and decoded. So we've got a few different sync words. The first one is for the link setup frame, that's the LSF in the beginning. So we've got the sync word and then the link setup frame. And within the link setup frame, we've got every information that is every information about the link that is about to continue in a second. So there is a destination ID, there's a source ID, there's a field that tells what is the payload of the transmission, and there is also a meta field that can be used for slow speed data transfer, like the geographical location or ID for the crypto or the nodes for the crypto. So the use of that is up to the application layer. And then after the link setup, we've got frames of data that just come one after another. And every frame is, of course, 40 milliseconds long. And every frame data starts with a sync word, which is different than the first one, just to differentiate between the LSF and the data. Okay, so when we have received all the 6 frames, that's called the super frame. And the reason for that is because when we start listening to the transmission, there are actually 2 types of joining the transmission. The first one is when you turn your radio somewhere here and you hear everything that comes after it. That's the first type. So you get the link setup frame, you decode all that information, and you know who's talking to who and what's the payload. But the second type is when you turn your radio when the transmission takes place already. So, for example, at frame 5 or any other number. So somehow you have to be able to reconstruct the link setup frame that is only transmitted in the beginning and nowhere else. So to do that, we split the link setup frame into 6 chunks, and each of the chunks is placed in the frame data. So when you get 6 of them, you can reconstruct the link setup frame, and you can tell if that transmission is of any interest for you, or you can discard it because it's for someone else. So this is the simplest form of M17 transmission, the string transmission. And the second image is from the previous version of our specification, and it lacks the end of transmission burst at the end. And this is just a sequence of a few symbols that repeat over and over. And this is to denote that this is the end of the transmission and nothing comes after it. Okay, so this is the link setup frame. From top to bottom, we've got, this is called the type of the bits. So type 1 bits is just the raw data that you want to transmit. This is just the raw data that is inside the radio, let's say. The stuff you want to send. So destination, source, type of the payload, the metadata, and the CRC. And after you have it, you have to encode it before you can transmit it over the RF channel. And the bits that are actually used for RF channel are type 4 bits. So before you get to type 4, you have to do some encoding, some puncturing, reordering, and randomization. But we are going to get back to that just in a second. So this is the link setup frame. This tells who's talking to who and what's the payload. Then we've got the voice frame. And the voice frame is a little bit more complicated because we not only have the payload that is encoded, but we also have that mixed with the link information channel, that is the link part right there. So that is the 1/6 of the LSF that I mentioned before. So any party that starts listening in the beginning of in the center of the transmission or at any part of it can reconstruct the LSF using the link information channel. And then after that, we've got the frame number and the payload. The payload is, it depends on the stream type. It can be voice, it can be voice plus data or data only. And actually, when we talk about data and voice, this is pretty much the same stuff because digital voice modes don't really care if I put voice in the payload or data in the payload. This is the same. Bits are bits, ones are ones, and zeros are zeros. And the tail at the end is for the convolutional encoder, and I'm going to tell you more about it in a second. So this is how the voice frame gets from the bits that are supposed to be sent to the bits that are actually sent to the filter and over to RF. Alright, so this is the simplified flowchart for how to get speech to the binary output. So we take the speech, we fragment it into 40 milliseconds pieces, actually 20 milliseconds pieces, because Codec 2 works on 20 milliseconds chunks of voice. So we take, as you remember, one M17 frame is 40 milliseconds long, and the Codec 2 chunk is 20 milliseconds long. So you have to take two chunks of the voice and encode it one after another to put it into one frame of M17. Then we chunk 1/6 of the link setup frame. We encode it so we are not afraid of the errors that come from the RF channel. We combine all this stuff together, encode the frame, and that's the output. This is basically from type 1 to type 4 of this and of this. So getting from type 1 to type 2 is the frame encoder, actually. Now, this is the least pleasant part of the presentation because I'm going to tell you something about the Galway encoding that we are using in M17. So the idea behind the Galway coding is that we've got a chunk. Well, we start with LSF, the link setup frame, which is 240 bits long. We chunk it into 6 pieces, and each piece is then 40 bits. Now, Galway encoder works in chunks of 12 bits. So actually, 40, it's not divisible by 12, so you have to add 8 to make it divisible. So we add something that I don't know if it's in the presentation. Actually, it's not very important, but we take the Galway encoder to encode the link information channel, and then we are using punctured convolutional coding for the rest of the frame data. So we are using two different methods for error correction coding inside M17. So this is the Galway coding we take. So we take 12 bits and encode that into 24. So I don't remember what the timing distance is for this code, but there are two different Galway codes out there. One of them is the perfect Galway code 2312, which takes 12 bits of data and generates 11 bits of parity bits. So we are taking basically that part that's generated by the polynomial above the matrix, and we add one extra parity bit, so that's the last column of the matrix. So actually we are getting something that is still Galway code, but it's called extended Galway code for the link information channel. So we encode 48 bits into 96, and those 8 missing bits that are extra are used for counting from 0 to 5, so we can tell which chunk of the link information channel we have just received and is in the frame. Then we've got convolutional coding, which is actually also used in NXDN. The same polynomials are there, but the puncturing scheme is slightly different. because when you have a convolutional code, you can end up in arbitrary number of bits for one bit input. So in our case, the rate is 1/2 because for every bit of input, we generate 2 bits at the output. And those generating polynomials happen to be the best and optimal for this constraint length. And in our case, it's 5 because we look at 5 bits. To be sent is about, let's say, 240, I believe, plus the tail bits that are used to flush the convolutional encoder. And so that's 244. And the process number 1 is the convolutional encoder, which has a rate of 1/2. So we end up with 488 bits, I believe. And then, as the frame is 40 milliseconds long, we've got only 364 bits for the payload, so we have to get rid of some bits to save the space. So we can't just, we can't transmit type 1 bits over the RF, we can transmit type 2 bits over the RF because there are too many of them. And if you remember, the bit rate is 9600, so it leaves, the sync word is 16 bits, so it leaves about 364 bits for the payload. So we have to get rid of some of the bits from the encoded payload to get just the right amount of bits to get transmitted over RF. And this is what the puncturing does. So we take 61 encoded bits and leave only 46, or from 12 we leave only 11. And we've got 2 different schemes because we've got 2 different setups right here. So the first puncturing scheme is the number 2 in this block. So we've got 488 bits and we have to get 364, I believe. So that's the puncturing scheme number 1. And the other one is for this one, when we got frame number, which is 16 bits, the payload is 128 bits, and tail is 4. So if you multiply by 2, you get the encoded payload length, and you have to get 364 minus 96, and I don't know how much it is, but you have to end up with that number. And it happens that the P1 or P2 encoding scheme, the puncturing scheme, just fits the best for that purpose. Then we've got bit interleaving. This is very important if we talk about combating errors that come from the RF channel, because they usually come in bursts. So you get, for example, 3 bits in a row flipped or missing, let's say, or even 4 bits in a row, or even more or less. And using a bit interleaver, you can just reorder the order of the bits in the payload, so such that even if there is a burst of errors coming from the RF channel, it gets spread over the entire frame, so the convolutional coding can actually help us recover that errors. So if we didn't use that, we would suffer from a lot of errors. And using this method, you can just spread them over the entire frame and have the error coding scheme do its job. there is also one thing that is required for FSK, and this is something that I would call a randomizer, which just makes sure that the stream of the symbols that is being transmitted has as low DC component as possible. So you've got as many zero crossings as possible and as many symbol transitions as possible. Because if we had a long run of the same symbol, that would mean the receiver can't actually lock to the signal because it has to know when to sample for the symbols. So what we do is we take a long 46 or 45 bits, 46 bytes of a pseudo-random sequence and use an exclusive OR with the data. So before transmission, we just randomly flip some bits to get a randomized bit stream. So this is denoted as 4 in this graph. And after this process, those bits are ready to be sent. Almost. Okay, so every pair of bits is called a digit. And just because we've got 4 FSK modulation, it means that we've got 4 different levels of deviation from the carrier. So 2 digits, 4 levels, and each digit maps into one symbol. Now, when we have the digits, we can map them onto symbols, then upsample it, filter it, and use it as the source of modulation for our VCO in the radio. And right at the output, there's M17 in RF. So I don't know if any of you are familiar with radio, but you can actually have a lot of fun, and you don't even have to possess a ham radio license to play with this. So basically, what this flow graph does is it takes the binary input from a file that is pre-encoded M17 bit stream. It reads it byte by byte. Then, for every byte, we convert the byte into 4 digits. Then we map it into symbols, filter it, and we are going to show how it looks versus time. So it looks like this. So the plot in red shows the raw symbol stream. So it's not filtered, it has a lot of steps. So you may think that the spectrum, the bandwidth of the signal in red is very wide. And in fact, it's infinite because those steps are very sharp. So after we filter the red signal, you come up with the blue one, which takes a lot less bandwidth as the transitions are very not as sharp. And it looks like this. So the red signal has infinite spectrum, left and right, and the filtered signal has all the power focused on the first lobe where all the energy goes, and that's where the data is. So we don't need anything that is right from that transition point. Now, this plot, this flow graph does something else. The first part of it is the same. We end up with symbols that are filtered, but this time we are not looking at the filtered output, but the frequency modulated output. So if you were to look at the spectrum of a radio transmitting M17, you would see something like this. So the blue plot is the filtered one. This is the actual M17, and the red one spans infinitely to the left and to the right. So we've got a lot of unwanted modulation comments that we filter out in M17. So M17 is the blue one. Oh, that's the fun part, to wake you up. So that's me in Warsaw transmitting M17 using a very simple setup and a very simple dish. And this setup actually, with this setup, I was able to transmit M17 using that dish up to QO100, and I was also able to get the signal back at the downlink, but it wiggled so much that I wasn't able to demodulate it. So I was able just to bounce it back and from the satellite. Yeah, it was QO100. We also
it's
QO100 is the one and only amateur radio satellite that is at the geostationary orbit. So it's 1/10 of the distance from Earth to Moon. So to bounce the signal, it takes about half a second, I believe. Okay, so that's the only satellite that is for amateur radio use that is on a geostationary orbit. So we were using M17 to bounce the signal off it. And that was in April last year, I believe. Or March, something like that. Oh, that's interesting. We have devised a method to convert pretty much any radio that is 9600 watt capable into M17 radio with just using a simple board that you connect to that radio and to a microphone speaker. We've got some with us, and we also have some other demos that we are going to show you later after the presentation. So this actually turns your radio into M17 radio. And we are also working on shrinking this down so it can fit in a microphone speaker. So it's very small. Right now it's a little bit bigger, but we are working on it. And I am the co-author of that board, and the other author is Matis DB9M80 from Germany. Then this is my first test for the Yesu FTM6000 receiving M17. So this is my best code. And the setup was very easy. I used an USRT B210 to transmit M17 signal, and then used the Yesu FTM radio for reception, and just a picoscope to plot the eye diagram at the receiver side. So it looks pretty clean, and the link is over RF, so we are not cheating. This is an actual setup. And the last part is the experiment that I tried to transmit at least 4 or 5 different carriers using one power amplifier, of course M17, and I tried to demodulate M17 using SDR++, which is an open source software, and it decodes M17 right out of the box. So we can just install it, enable the M17 decoder, and you can see the source call sign, the destination call sign, it decodes the channel access number. So I was able to transmit 5 independent carriers, M17 carriers, using the radio and receive it with SDR++. So you can't hear the picture, but there was audio coming from the speaker. And to sum everything up, after a long time of stagnation, we finally have Codec 2, which enables us to play with digital voice modes, not only on HF, but also on VHF and up. So after a long time, we finally got something that works for amateur radio, and we are bringing back the power to us to innovate. And thank you, that's everything from me. Okay, so Nico, you can finish them.
Okay. Thank you for attending the event, and we have we brought all our toys from home on the desk here, and we can show you that the thing that we described actually work doing a simple voice link between two radios. So if you want to stay in contact, basically to get involved, even if you are not yet ham radio operators, we have a Discord channel. We have two Discord channels, one of M17, the other of OpenRTX, and they are accessible from our website. Basically, we have also some Twitter accounts in which we deliver we show the cool things we do. So these are the ways basically to stay in contact. And in general, here in Polytechnico, there is a Polyham, which basically is hosting this event, and I am a part of that association, and we meet, but you know, when we want, so every couple of weeks or even less than then, and basically we try to work on some projects, but everything is pretty much driven by what's making us passionate about what we want to do. So having said this, I would terminate the YouTube stream, and we can proceed with the demo. Okay? So thank you also to anybody who attended the event from YouTube.